And yes, it is so wonderful to have Anne Tomlinson with us today. So Anne is a geologist and geophysicist with a specialization in potential fields and interpretation. She joined Southern Geoscience in 2005 and has been there ever since. And after 9 years as a principal geophysicist, she stepped into the managing director role in 2021. And it is going to be awesome to get the latest insights from her about exploring new horizons, magnetic surveys with drone technology. So strap yourselves in. It's going to be an awesome session. Please keep using the chat and we'll open up the floor at the end. And yes, thank you so much, Anne, for joining. It's amazing having you here.
Thank you, Jess. So yeah, thanks, Jess. Thanks so much for the invitation. This is a specially put together talk for this for GeoHug this morning. We had a look at some of the I sat with Jess and had a look at some of the requests that people have put through for topics in the geophysics space, and potential fields is one of them. So that's a specialty of mine that I was happy to talk to. And I thought the topic of using drones in geophysics and specifically magnetics was one that would be of interest, and it's certainly something that we've sort of had a bit of a, I'll call it a backseat involvement. I'm not directly involved with the acquisition, but it's something we've been watching here for a few years now. And I sort of every now and again I do get asked about what sort of new innovations in geophysics are with geophysical exploration, and I think drones definitely as an acquisition platform can be counted as one of those innovations. Has it been sort of an overnight disruptor? I don't think so. Not yet. It's not replacing other systems that we've got, and we'll look at that today. But yeah, I'm going to go through a pretty high level overview of how drones are being used sort of in mag acquisition. And I do want to I'm going to jump straight away here to the endpoint, which is sort of my key takeaways that I hope everyone will sign off with today. Firstly, drone mag acquisition, definitely I count it as a genuine developing technology, but not to say that it doesn't come with quite a few technical and sort of logistical challenges that we'll look at. And secondly, the big take-home point there, don't treat it any differently to acquiring magnetic data from any other platform. You need to understand the system and its limitations, understand your target, and definitely optimize your survey design. So I'm just going to sort of step through this discussion in three parts. I thought I'd kick off with a bit of scene setting on what that use case for drones is. What are those overarching reasons or advantages to acquiring magnetic data with a drone? Then I'll run through sort of in that second part really where we're at the moment, look through what the current commercial systems that are running look like in terms of sort of their development. And then I'll sort of, within that, we'll get back to some basics on mag survey planning, because it's a really big piece there. And I've got about 3 case studies, little real world examples of some data with some comparisons of other platforms to look at as well. And then I'll sort of wrap up at the end there with what sort of the future holds, where this tech might be going. But to get a little bit interactive, Jess, if we can get that poll running, I thought I'd see what everybody had. If you had any thoughts on this, you might have been involved in the survey already. You might have just thought about it. If you haven't, why would you consider using a drone? What do you think its advantages might be? So yeah, I'm interested to see if you can see that poll now. Just start giving some options. Now, let me have a look. What's that last answer? I'm curious to see what that last answer got. So we've got cost efficiency at 19%, accessibility, yep, 27.
I like new tech, 6%.
I like 6%. Okay, I was going to talk to that one. So I'm just going to, I'll jump in and say, I hope this isn't the only reason people are doing it, but I have heard of people using drones for that kind of novelty factor. I get it. I mean, they're kind of cool. They're pretty futuristic, but alone, that's probably not the right reason to just go with the drone survey. You do need to consider what's going to get you those optimal results for your target and all your application there. And there are logistical hurdles that a drone platform certainly can help with that other platforms might not be able to, but it can go in reverse as well. So just because it's new doesn't mean it's necessarily the best option yet. So looking at those options there, I think there's probably a pretty good cross-section of those, what we think drones have to offer in this space versus some of the other conventional platforms. And by those, I mean, we've got, well-established, fixed-wing aircraft, helicopters, and then obviously ground-based sort of walking mag. So these are all really valid. I have crossed out that last one there, like new tech again alone, probably not a great reason to do it, but there's discussion to have around each of these factors here. So I'm going to just walk through all of those points just on these coming slides. I did actually, get a bit of AI involved here and ask ChatGPT to come up with a bit of commentary. So that's what you'll see on the other slides. And I'm just going to talk through each of those. I've coloured some of the key points sort of in a bit of a traffic light system. So of those advantages, so something's green, I agree with it pretty well. Those orange features are come with a few caveats and challenges associated with them. And there's one or two red items in there that I would say I probably disagree with, as in, where current technology is at and that practical application of this. So kicking off with safety, I really think this is probably one of the biggest, most significant advantages that drones give us. I dare say anyone sort of involved in the resource industry or even just in remote operations long enough, you probably know of someone directly or even just a degree of separation has been affected by an aircraft-related incident, unfortunately, in remote locations. So I do see safety as a major driver in that continued development and implementation of this tech. And I was listening to a podcast the other week on this topic, and someone described it that use case of drone geophysics as really being for sort of dirty, dangerous, and demanding jobs. Cost efficiency is an interesting one. And I am talking, so, the examples I show today are all Australian examples. I'm based in Australia. That's the lens I'm looking through. And we are very privileged here to be exploring in pretty generally wide open, low relief regions. And we can deploy these low cost fixed wing systems, pretty effectively and cheaply. So that cost case for drones in Australia isn't quite as clear cut. Drone systems can come at sort of 3 to 10 times the cost of a fixed wing system, sort of on that per line basis. And we also in Australia have got probably world's best government open file magnetic repositories, that give us that continent wide coverage. But I have worked on data sets in places such as Canada and seen work in South America, where you need to deploy helicopters to areas, whether it's because of, access, terrain, forests, lakes, swamps, all that kind of stuff. So that case for commissioning a drone survey is certainly a lot stronger. But if you have a small area that you need to get coverage over, mobilizing a larger airborne system or maybe even a ground crew, access might be a problem, and that just generally might not be practical from a cost or a time perspective. So that drone option is a good one. Accessibility. So I think the fact that you can pretty much pack up a drone and a system into a kit that you could likely throw on the back of a ute is a pretty good advantage there. From the altitude argument, yes, they definitely can fly lower than most manned aircraft. Practically speaking, though, the flight path that we put in for drones, and that height that they fly at are pre-programmed. They do rely on existing elevation models in order for that, to safely plan those flights. As it turns out, drone pilots really don't like crashing their drones, so they get a bit conservative sometimes as well. So it's not uncommon to sort of take that highest point in a survey area, and that might be a few isolated trees, and then simply plan your survey at a drape across that. So there are certainly still some challenges of actually getting people to be able to fly that system at that lower clearance off the ground. And I'll talk a lot about that terrain clearance. And yeah, I've also seen some of these, systems we have to miniaturize a lot of these, and that getting that accurate drape and also knowing where that sensor is above the ground isn't necessarily controlled as good as it could be. So that's a challenge there. We really do need to know where that magnetic sensor is above the ground in order to do that data processing, and also for a lot of that modeling down the track. So yes, we can, drones can fly low. I'm gonna click through here. I have yet to, on the densely forested areas, I have yet to see a geophysics drone survey flown through forested areas. That's why I've got that marked in red, not to say that couldn't be a future piece there. And because a lot of that does, probably involve manual control of the drone, and as it is, most of these are flying fairly autonomously. On the rugged terrain side, I definitely thought that was, early on, I sort of started looking into this, I don't know, 5 or 6 years ago now. And I thought that was going to be a huge piece on the capability for drones. And I think it still is. Like I said, in Australia, we don't necessarily have as much of that rugged terrain issue as you would in, again, other areas like, say, Canada, South America. But practically speaking, there are still challenges to that. I talked about the elevation models. They're not necessarily always available or required. That radio link, so it's maintaining that radio link as well between the pilot and the drone, that can be challenging. There is requirement to maintain that visual line of sight. And the drone, the operation of drones is governed by aviation law in Australia. This falls to CASA. And like I said, they require that visual line of sight, although more and more operators, I think, are getting that beyond visual line of sight authorization. In high altitude terrains, drones certainly, I think, present as a good option. If you need to deploy, fixed wings obviously can't fly in really rugged terrain. They can't get that good performance unless you do just want to fly it really high. You need to deploy helicopters. They are expensive. Some helicopters do have altitude limitations if you are really in quite alpine, mountainous regions. And there's other, obviously, challenges in terms of vegetation and visibility. I dare say as well, of course, there's the safety factor as well, in terms of flying in that rugged terrain. There is a pretty slim chance of recovering a drone once you've lost it in that kind of terrain and dense vegetation, but again, I guess better to lose a drone than to lose a manned flight. And that leads to these, operators often sometimes going conservative on those flight specifications. I did have a couple pics here. So I was, again, on another call last week, and I've grabbed a couple of these pics here. This is, and I thought it was quite a good example of showing how people are working around getting that pilot. So in this case here, this is in Sweden. Just credit to Dr. Bastani there from the Geological Survey of Sweden. They've been doing some UAV MAG and EM flying. And what you see here is they've decided to get a sky lift and stick the pilot 26 meters up into the air. So that's sort of a workaround there from getting that line of sight, I believe, and that link with the drone. You can just sort of see the in that one of those images there, you can see that multicopter there with its towed bird underneath it. So they call this sort of rugged terrain. It certainly is, but it's not high altitude, I think, but they're obviously dealing with some fairly tall forested areas there, as well as some relief. And I thought I'd just on the densely forested piece, there is, play a little video. I don't think you can hear that, but if you can, it's a buzzing drones. But there's still, again, a bit of a future piece. This isn't geophysics, but it is drones, flying, not manually manned, but they're using a lot of clever, algorithms here for them to do sort of this, collision avoidance on the fly. So there's certainly, evolving developments in that space. Whether we can, at the moment, no, we probably can't stick a mag sensor onto the base of one or underneath one of those drones. But there's definitely a lot of work being done in that space there. Looking at sort of that flexibility and maneuverability, I think on both of these points, there's good advantages. Again, I haven't probably seen them practically applied yet. Surveys are still pre-planned. We don't really modify much during survey in terms of what we're seeing in the data, unless we are just considering perhaps infill lines or extensions to the survey coverage. We've got there flying at variable altitudes. Obviously, we can, the drones do offer that as an advantage. I did touch on, the challenges that getting lower. There are some practical limitations. There are also some height ceilings from a regulation perspective. There are maximum heights that a drone can operate at. I know this is the case in Australia, and I expect that's probably the case in other parts of the world as well. There is some that does from a data quality and some of the ways we do QC the data and check it, and high altitude flying is fairly standard to do in traditional platforms. It's something that's a bit limited because of this regulation here in Australia. On the real-time data collection, I'd probably say there's a bit more of a future piece there. Again, I haven't seen collecting that or seeing that data really in live feeds and adjusting on the fly. But I'll talk to that sort of at the end in terms of some of the potential future applications there. Sort of all green here. I think that environmental impact is, a drone is certainly significantly smaller from that kind of carbon footprint emission standpoint. Potentially as well as noise and ground disturbance compared to some of the airborne platforms. Not to say that this doesn't obviously negate the need to do all the usual community and landholder consultation. Deployment, absolutely. These are pretty small systems. Good advantage there. I do know, I'm pretty sure in Brazil, for example, if you want to bring a fixed-wing aircraft into the country, you need to deregister it and then re-register it in country. This is sort of pretty time-consuming and expensive. So there's an advantage to be able to use drones there. That being said, there will be, jurisdictions in the world where importing drones is fairly sensitive from that kind of security perspective as well. So I guess there's a lot of it's pretty rapidly changing in that space in terms of regulation. My last point here I've sort of deliberately left till last, and it really is a key one that we'll talk through today, is that resolution. Drones certainly can collect high resolution data, but it's not a given. It does require good effort, a significant effort and technical input, both in terms of understanding the geophysics involved, specifically, how you can acquire and deliver good quality geophysical data, but also that need in the survey execution from the engineering and drone piloting perspective. So it's marrying the best of those two. So I wanted to sort of, emphasize, what makes, what gives us magnetic data resolution. This is dictated by these factors here. We've got the sensitivity of the magnetometer. We've got the signal to noise ratio, and the noise I'll talk to more in a second. We've got the sample rate, so how frequently are you sampling as you're flying along, your line spacing, your sensor clearance above the ground, and those just three last items there, that sort of really adds up to what your data density is. So with the signal to noise ratio, it really is quite crucial. So we've sort of spent some, probably in post-World War II, sort of 50, maybe closer to 75 years developing and refining magnetic data acquisition methods, from those traditional fixed-wing and helicopter platforms. So let's not think that we can suddenly put a new platform on the market without needing to put sort of significant effort into understanding that system and understanding the noise and being able to manage that. The noise itself, we're talking about, it can come from surface culture. This might be infrastructure. We can have geological noise. And then we obviously have noise from the platform itself. The first two, I would say that we could manage through good survey planning and understanding your area and target. But the system noise is certainly the big one that needs consideration. This has been a huge focus, in the most recent developments. And drones, as you can probably imagine, have a significant amount of electrical and magnetic noise that interferes with the signal that we're really after. So just to sort of reiterate this point, drones don't necessarily provide a high resolution magnetic data set without all due consideration to all of these data resolution factors, just the same as you would if acquiring magnetic data on any other platform. So that's sort of my setting the scene on that sort of use case and advantages there. Takeaways here. I really think that drones do have that strong use case from that perspective of safety, environmental impacts, and deployment. But there's certainly still challenges with the accessibility and data resolution, but not to say that these certainly aren't unsurmountable by any means. So where are we at? I'm going to sort of look through, I'm just going to show some pictures, look through what sort of the commercial systems that are operating look like at the moment, what they can achieve, and what you need to consider with them. These considerations certainly cover that cost, logistics, as well as that geological, that target piece. I'm not going to do a whole history on this, but in terms of sort of systems that are operating at the moment, what they look like, From a platform perspective, multi-copter drones seem to certainly be the most common platform that's being used in the market. Power sources for these, there are some that are battery only. So they've got sort of 20 to 30 minute flight durations. I believe there could be some advancements happening in that space. Some of these are fueled systems as well. So then with a fueled system, you'll get significantly longer flight times. You can get on the order of 2 to 3 hours. You can also get hybrid systems, as I understand it, so battery and fuel combinations. You'll see here, there's sort of multicopters, there's quads, hexacopters, a few different systems there. There are some rotor as well as fixed wing systems. So there's a variety being used. I was involved with a drone survey in Canada in sub-freezing temperatures, and it's just a bit of an experience I had there. Didn't appreciate the impact that extreme cold has on battery performance. So in an extreme cold there, you can sort of get battery life almost halved. So that's sort of like one of those sort of technical logistical considerations with quite a big impact on survey productivity. In terms of the sensors people are using, most commonly these are slung beneath the platform. That's to help provide that separation from that electrically and magnetically noisy drone. There's some turnkey sort of sensor systems that look pretty slick. Things like I've got showing here that Geometrics have got a mag arrow. Gem is another manufacturer there. They've got something called the Airbird. There's also some sort of simple sensors that just get slung beneath the drone there. A lot of these have got sort of cabled, they're on loose cables beneath the drones. I have seen one system on display in Canada that used a rigid boom. And there's one platform here in the middle there, that Drone Geoscience one, which looks like a fairly rigid boom. When you get a swinging bird, you start inducing quite a bit of, that motion induces noise as well. So, looking at sort of making that a bit more rigid aims at trying to reduce some of that associated noise. But yeah, lots of technical factors there. So there might even be some that have I think the Canadian system I saw has almost like a stinger mounted, so it sort of sticks out the front. This central one here is obviously suspended beneath the drone. So that's really sort of the systems that are in operation. They're a bit of a snapshot. There's quite a few out there. It's not exhaustive. You can have a look around, but that generally covers most of what they're looking like at the moment. What I do want to touch on, because I think it's pretty important to this data resolution discussion, is just sort of stepping back and looking at some fundamentals around, what controls the outcomes and success of any, I'll call it any aeromag project for that matter. Firstly, we have that safety piece, so it's the safety of any flight crew if we're talking about a manned survey, as well as any occupants within that survey area. And as I touched on in the beginning, I think that safety card is probably a pretty decent differentiator that drones are going to offer. Other factors that we have here, we've got line spacing, we've got survey height, flight line orientation, survey shape, topography, altitude, climate, atmospheric conditions, the regulations, and even the politics. So these will all control sort of how successful any project can be, whether it's drones or fixed wing or helicopters. So touching on here, the flight height and line spacing in particular are, I think, two key factors really in what you want to consider for that optimal platform for any given survey. So your flight height selection has to take into account that safe operating height, any regulated distances or clearances from any infrastructure, considering local terrain, platform performance capability, as well as then the depth of your magnetic basement or your target. In some cases, there's no point flying certain, getting closer and closer to the ground if you're looking at quite a deep target. You're not actually going to get a material improvement in the data. For ideal sampling, your line spacing as a rule of thumb should be approximately your sensor height above ground level. So if your line spacing is closer than this, you're probably oversampling and adding unnecessary expense for minimal gain in the data resolution. If you go wider than this, you do risk undersampling and not being able to resolve those magnetic features of interest. You can also get aliasing when you start gridding up that data. And that can be also problematic. We've seen undersampled data in, for instance, low latitude regions where you want to apply a reduction to pole algorithm, and that math starts to fall over and you can get artifacts introduced. As a rule of thumb, I mean, it's not always one-to-one, but generally I probably wouldn't recommend going wider than about 4 times your sensor clearance in terms of your line spacing. So there's a bit of an example here in those images. You can see that top left one, we've pretty much got a 1-to-1 flight height to line spacing ratio. And as you step through there, we're going to sort of 1 to 2.5. That's not bad. We'll probably say that that's good sampling. Then we get to that, 200-meter line spacing at a 40-meter height, and it's starting to fall over a little bit there, not so good. And then if you're flying at 400-meter lines at 40-meter height, it really is pretty poor spatial sampling there. So that's sort of just a bit of a touch on, things to consider, with planning any mag survey. So I've got sort of 3 examples that I want to walk through here. They're pretty short, but it's good to see some real world drone mag data sets. These are compared with other mag data sets over the same areas, and they illustrate, a lot of those data resolution points. They are all from Western Australia. That's obviously where I'm located at the moment. And the first one here is, this was an area chosen as pretty close to Perth, a bit of a test range for this company. It's the McPherson's Iron Project. It was held at the time by a company called Northern Iron, now called Northern Resources. So thank you for permission to them for presenting this. The area itself, it's over quite a magnetite-rich iron formation, so good mag target there. And we do have 3 magnetic data sets that are across it. We had a fixed wing magnetic survey. This was flown on 200-meter space lines at 60 meters above the ground. There was some ground mag done on 100-meter lines, and that one had probably the sensor about 2 meters, so walking mag 2 meters above the ground. And the drone magnetics were flown on 25-meter space lines at 30 meters terrain clearance. So just to point out, none of these were collected exactly the same specifications. And so that's a factor when we look at the images and the data. And if we just think about what I was covering on the last slide there in terms of sample quality, the fixed wing data, you could probably count as pretty good. Ground mag, pretty poor, which is often the case in ground mag because you're so close to the ground. And the drone mag was pretty good, almost at 1-to-1. On the right, on this figure here, you can see the flight paths, survey paths for each of those surveys. Those obviously white space lines in green there are the fixed wing, the tight lines in blue are the drone mag, and we have some of those red lines with the ground magnetic lines. So all roughly flown on the same or walked on the same orientation there. So this is the data. These are stack profiles of the total magnetic intensity. So we're looking at line data, but just projected in plan across the lines there. So you can sort of get a good picture of how that, you can see that magnetic, hopefully you can see that blip in the magnetic units through the middle there, and see how the different sensor heights. So that is a big factor here, is that height of the sensor above the ground, not just the platform that it's flown on. And how that affects, the definition of the magnetic feature through there. Obviously, the ground mag has the noisiest data because it's closest to the ground. You get a lot of superficial noise as well as a few system things in there. Drone mag sitting in the middle in terms of resolution, and the lowest resolution there with the fixed wing. All of these are shown at the same scale as well, so it's a good comparison. If we grid that data up and make some images, this is obviously probably the most common way we visualize magnetic data. Again, we're looking at the TMI. You can certainly see that change in detail between the different platforms. The ground mag does capture that additional detail along the line, but probably that line-to-line continuity is less than the more tightly spaced drone magnetics. And you can sort of, you can see that it's picked up a bit of that detail there and that noise, but you definitely get sort of that continuity in the drone. And I quite like this profile comparison again, just to sort of see how well you can define a magnetic feature. So here we're taking just a single line of the data from each of the 3 surveys. It's a bit similar to the stack profiles before. We're just looking at one line. Ground magnetics in blue there, definitely the most amount of detail. You can obviously see that noise on the flanks of that main anomaly, but it's got highest amplitude. It's got 2 little peaks there, so it's picking up detail that the other systems haven't seen. Drone mag sitting in the middle there, that's sort of coloured in green. What we did do is a bit of an exercise is we took the ground magnetic data and we upward continued it to this equivalent height as if it had been acquired at the same height as the drone. So a bit of a algorithm there, and you can see that it's pretty comparable. So you get rid of that noise, and the upward continued ground mag in red there is pretty similar response to the drone mag. And the fixed wing obviously has that lowest resolution of the 3 surveys. So my second example here, again, sort of test flight area not far out of Perth. This was drone magnetics acquired by a company called Sensoram, who were sort of starting out in the space. They just sort of wanted to test out their system. They were flying a quadcopter with one of those mag arrows as their sensor. There's 2 magnetic data sets to compare here. So we had the open file 200-meter line space data that was flown at a 50-meter mean terrain clearance. And then they've come in and collected a small block of drone magnetics at 50-meter line spacing and 25 meters above ground. So they really wanted to just assess the system, compare it with the existing data sets, make sure it made sense, and also just look at some of those specifications and the quality of that data. So just looking at the results there of the images, here we have 2 images of the TMI. The flight lines that are overlain there on both images are the drone flight path. Pretty good, met the QC specifications that they set, and you can absolutely see the high resolution of that data, that mag data on the left there. Bearing in mind as well, of course, the specification differences in that it was flown at a quarter of the line spacing of the fixed wing. It was also flown at half the terrain clearance. So, but nice clean data there. And then just a little third example here. This is a example over near a historical gold mining area in the Murchison of Western Australia. Thanks to Rocks Resources for permission to present this one. This is a gold project. Gold mineralization here generally occurs near a granite sort of greenstone contact, but what they had done at the time is identify some additional mineralization further out into the granite, which was of interest. The granite itself is pretty weakly magnetic. You can see the image here that you can see is both of these cover the same area. In that sort of southeast corner, you can see the edge of the greenstone belt. So it's got quite a few quite strongly magnetic iron formations and ultramafics that dominate the response. The rest of that purple area is across the granite. So pretty dead, pretty hard in this to see detail. What we wanted to do is see if we couldn't map out any sort of controlling structures inside that granite to assist with any targeting. I like this example because we've still got 3 mag surveys that are much closer in overlapping specifications. So we've got there's a fixed wing survey, quite a high resolution one, flown in the mid-90s there, 1996. They flew this on 50-meter line spacing and a 40-meter terrain clearance. And so well sampled data set. I've actually got 2 drone surveys. So this is an example of 2 sort of side by side. The first drone survey was flown in 2019. That was, I'd say, probably one of the early commercially available ones. Pretty early in the technology. That was flown on sort of what I'd call ultra detailed line spacing, about 20-meter line spacing, and averaging about 45 meters above the ground. The following year, there was a second ultra detailed drone survey flown. That was flown on 25-meter line spacing and 25-meter terrain clearance. So pretty ideal sampling there. That second drone survey was just quite a small test block across the granite itself. So as I said, so on the right here, we've got an image of the TMI from the fixed wing, the 96 fixed wing survey, and you can see the flight path there in the bottom right. What I have done on the next slides is showing quite a nice side-by-side example of the 3 mag data sets. I've subset all of them just to the extents of the red flight lines you see there, which covers the most recent drone mag survey, just to get a really good comparison. So here we have all of the 3 data sets going from left to right. We have fixed wing, and then the 2019 and then the 2020 drone mag data sets. As we go sort of top to bottom, we've got equivalent images here. We've got the TMI, just a shaded linear image. The central row there, we've got a first vertical derivative with sort of a non-linear stretch, just starts to enhance some of the detail in the data sets. And on the bottom, we have a grayscale of the first vertical derivative as well, which is not a bad one to look at if you want to sort of highlight warts in any data set. I guess obvious things to sort of point out here, we do, in that central and that first drone survey, unfortunately, we do have quite prominent line noise interfering with seeing a lot of that signal through there. So it did struggle to get to really, control that terrain clearance, understand where it was. The system only had its sort of GPS. It didn't have any sort of terrain clearance. Modern fixed wing systems and helicopter systems will have sort of a radar or a laser altimeter to be able to control that terrain clearance. So that was sort of not well controlled, and they did only achieve sort of an average of about a 45-meter terrain clearance. Now, flying on 25-meter lines really does mean that it was quite heavily oversampled. So really sort of, flown too many lines and was needed for that clearance that they could achieve. Looking at that second drone survey, cleaner data presented here, good data quality, and you can just start to, really see the geology in there. And you can sort of, if you compare that 2020 drone survey with the fixed wing survey there, definitely sort of good improvement there. Can't say that, unfortunately, that second survey was really improved on that first one. So just really nice to be able to see those examples there of how they compare. So sort of wrap up a bit of that use case into sort of where you might apply the different summaries. And this is where we stand today, I'd say, in terms of the technology and what's commercially available. Lots of variables to consider. The costs I have sort of put in here are Australian sort of values, and these even in Australia sort of certainly do change and will scale with depending on survey size. But generally, if you want to look at, applications for fixed wing platforms, they're definitely best applied sort of over flatter terrain, large areas. You do get the radiometric data with them. I know that's standard in Australia, not necessarily standard in say Canada, and at the moment definitely the most cost effective of these three platforms. Drone mag, you can definitely tackle more difficult terrain in areas where you sort of can't get low level manned aircraft into. Gets that big tick from that safety perspective, being unmanned. You are dealing with shorter flight durations, so you need to have that proximity of the pilot to the system. So that does make them better for smaller survey blocks. You might have a remote area if you simply can't get, if you can't drive into that area, you're not really going to be able to fly a drone survey at the moment. You're still going to have to, if you've got an airport further out or a runway on an area, and I'm thinking of places perhaps like the Amazon when you're flying surveys and you simply can't get in there, you're going to have to be able to use larger systems to be able to sortie out to those areas. Ground magnetics definitely best suited also to smaller areas and probably shallow targets. They do give that highest resolution line data, being having that sensor closest to the ground. And most easily acquired in open terrain. I guess on the drone mag as well, if I point out, again, difficult areas to get into. You could also be dealing with, getting into swamp areas and you want to get low. Just tricky areas in general. So that's probably a bit of a general, good overview there on where you might. And there's overlap in all of this, and just like I said, lots of considerations to take into account. It's not one size fits all. You definitely want to assess every survey area and what that target and objective is to be able to apply the best platform to that. So takeaways, as I said, just assess the suitability of drone magnetic surveying, considering your cost, the logistics, the target, and that's not necessarily in priority order. You can get good quality data. We know what good mag data looks like and how to plan a quality survey, so we don't want to sort of regress on that front. I recommend using an established and reliable operator. They're out there now. It's definitely developing quickly. And if you need, get that independent specialist to help you out with that survey planning, management, making sure the data QC stacks up. So apply industry guidelines to survey tolerances and data quality, and I will expand on that a bit next. But it is an exciting and valued tool for the right application, for sure. So my last section here is not too long. I really just sort of wanted to see, where are we going with all of this? What does the future of drone magnetics or drone geophysics look like? I just touched on that last part there, industry guidelines. So there are actually industry guidelines for drone magnetics that have been established. There's a technical group, it's a bit of a mouthful, called the Near Surface Geophysics Inter-Society Committee on UAV Geophysics. They arose out of there was a summit on drone geophysics in 2020 held by the SCG, the Society of Exploration Geophysicists. And they really recognised in those discussions that there were many drone users out there who weren't experienced in geophysics, but they were increasingly developing drone-mounted geophysical systems and acquiring data. There are also quite a few geophysicists who were new to drone geophysics. They might have come from, terrestrial surveying or other airborne surveying backgrounds. So in general, it was a pretty, it was a big learning curve on how to best acquire quality data. And there was data coming out of those surveys that seemed to be lower quality standard than where we really, the industry was used to. And they saw that need to address that for the benefit of the reputation of the geophysics industry, as well as protecting, those clients who were actually paying for those services. So in 2022, that group published the first version of the drone magnetics guidelines. It's not a standard, but it is guidelines. There's a QR code there if you're interested to follow a link to their website. They do cover, it is for drone geophysics in general. There's a few other platforms there. And the aim of that really is just to help maintain that reputation there. I think educating the end users on how to best apply drone magnetics is a big piece, and that's sort of what I'm presenting today, understanding, what's fit for purpose. I've touched a little bit on some of the regulations, but I haven't gone into it in too much detail, not my expertise, but it is certainly rapidly changing. In many jurisdictions, that legislation on drone operation does limit large-scale commercial applications of geophysics. You need that, visual line of sight is a bit of a limiting factor. But, I mentioned operators are getting licensed for beyond that. So I think that's going to be an evolving space, and people are catching up on that. I showed that video earlier. So I think developing active collision avoidance, I know this is happening, with some people, so being able to, or, we call it real-time sensing or real-time sense and avoid. So developing in that space is going to allow systems to be able to fly lower with more confidence, so less risk of damage or system loss. So I think that's certainly an innovation that's going to keep evolving. This is so miniaturization of sensors, that's a big part, a big R&D area. You need those smaller sensors because of, just to combat those payload limitations. These smaller drones can only carry so many kilos. Definitely continued development there. And that does extend beyond magnetics into other sensors such as radiometrics, hyperspectral cameras, gravity, EM, and even GPR. Amira Global completed a project on this topic in 2020, and that report's publicly available now, so it's an interesting read if you like that. And these last 3 points here really probably are getting into that blue sky realms. Just some ideas there on sensor arrays or swarms. This could look to sort of break that traditional approach to geophysical surveying, which is sort of, go in, do straight lines, parallel lines, perpendicular generally to sort of the strike of the feature that you want. I think the idea of swarms or array sensors, could allow for magnetic data to be measured, at multiple altitudes or multiple locations simultaneously. That might be able to help with better magnetic, source definition or separation of responses. So I think there might also be able to be, there might be a bit of a productivity or efficiency piece in there as well. On the, AI, machine learning, you can't really avoid that discussion. It's sort of in the news and everywhere on a daily basis at the moment. And I fully expect AI applications to get involved. It might be, in the data processing workflows, and it might be part of that, that real-time processing piece. I don't see it happening in actual sort of commercial surveys at the moment, but I think that's definitely an area of research. And lastly, this is really also sort of tied to that real-time processing idea, is that being able to inform a drone where to survey next, so sort of almost that like dynamic survey design, it sees the results and it knows how to modify a survey. Not my expertise, but I think edge computing capabilities might sort of be part of enabling that. And that really sort of has a bit of a disruption there in terms of that traditional way about how we've gone about, planning, executing and analysing mag surveys. So that's really it from me, I think. I think I've covered a bit there. Just a few acknowledgements there to some people who I've had lots of conversations with us about, and colleagues past and present, as well as operators and innovators in this area. Yeah, as I said, thanks to Northern Iron and Rocks Resources for permission to present some of that data, and a few little background resources there if anyone's interested.